but wholly inconsequential, I have to ask you, are you a tea or a coffee guy, Chuck?
Actually, I drink neither. I used to drink a lot of coffee, but it started to give me headaches. So I upon consultation with my doctor, I quit drinking coffee. So,
Well, you might not be a tea or coffee guy, but you are an ALD guy, so that's the important part.
Welcome to ALD Stories, a series of conversations where we share the untold stories of atomic layer deposition and the people behind the technology. This podcast is brought to you by Venec, the home of ALD.
Hi, everyone. Thank you for tuning in. Grab your coffee or your tea, and welcome to another episode of ALD Stories. I'm your host, Tyler Myers, and today we have a fantastic guest with us, Professor Chuck Winter from Wayne State University in Detroit, Michigan, in the United States. Professor Winter is the Associate Chair of Chemistry at Wayne State University, where his research focuses on the design and synthesis of novel ALD precursors. Chuck, thank you so much for joining me today.
thank you very much, Tyler.
Part of the reason I was excited to have you on here is your background as a scientist and your training as a scientist is maybe a little bit different than people might expect for ALD chemists. A lot of us nowadays are material scientists, we're physical chemists, and are coming from that side of the field. But if I recall correctly, your PhD was in organic chemistry. Is that correct?
That is correct. I worked for Paul Gassman, who is a physical organic chemist. And I did organometallic chemistry with him, but it was definitely an organic chemistry group. I was, one of two or three people not doing pure organic chemistry in the group. And so then what I did is I went and I wanted to do more organometallic chemistry. So I did a postdoc with John Gladys, and I got the job at Wayne State University. And I found out very quickly that organometallic chemistry was very competitive for funding. And so I started looking for other areas where I could make a contribution. And I got connected with a scientist at Ford Glass. And at the time, they were interested in making titanium nitride coatings for glass. And so I collaborated with Ford Motor Company for about 7 or 8 years on titanium nitride CVD. And so I worked on CVD for about 10 years in the first 10 years of my career and made precursors. And it was about in the late 90s that it became clear that ALD was emerging and was going to become a very important technique. And so that's how I got into, of course, I'm a synthetic chemist by training and interest. And so I was very interested in making ALD precursors. And so that's how I got into the field.
So you were doing CVD long before ALD was really largely known, before it was wholly relevant. It was very, very much isolated to the display industry at the time, back in the 90s and late 80s. When you started seeing ALD emerging, did it just feel like a natural step to go from designing precursors for CVD to designing them for ALD?
So I became interested in taking what I knew and trying to get into the ALD area. And so there's two aspects to ALD. Is you have to make appropriate precursors. And then number two is you have to test them. And so I had no trouble in my laboratory making precursors because that's what I do. We're designing precursors. But the one missing piece that I had was the ability to test precursors. And so what I had been doing is I had been following the work of Lauri and Niinistö at Helsinki University of Technology, who was one of the few academics in the world working on ALD at the time. And I happened to be at a Gordon conference, and I was talking to someone and I hadn't seen, and I asked her, so what are you up to? And she said, well, I'm on a Fulbright scholarship in Finland. I said, oh, what lab are you in? And she said, oh, Lauri Niinistö. And I go, oh my God. So I said, can you go back to Lauri and tell him that I'd be very interested in talking to him further, and that I'm very interested in making precursors, but I don't have any deposition capabilities. So Lauri and I had a phone call, and he invited me to come to Helsinki University of Technology, give a seminar. And then I sat down with this group, and basically we decided that we would collaborate. And basically I learned ALD, the how to do the depositions and how to interpret the data, what tests you need to run to establish ALD processes, how to analyze the films.
Hmm.
I learned that through this collaboration.
And what year was this that you had
I
initial?
would say that around 2000 or 2001 was.
So you were making them in your lab at Wayne State and then sending them to Finland to be tested. Is that right?
That's correct. That's correct. Yeah.
Well, let's start diving into the research then a little bit. So let's start talking about precursor design then. And could you walk me through, just to start, what makes a precursor suitable for ALD? What properties do they have? Why is TMA, trimethyl aluminum, and things like titanium tetrachloride so good at doing ALD?
Let's start first with the basics. So a precursor needs to be volatile, so that you can, needs to have a vapor pressure of, probably at least 0.1 torr at a below a couple hundred degrees C. Hopefully a lot more than that. And that's so that you can get a saturated gas stream to pass over into the reactor chamber and over the substrate. Secondly, the precursor needs to be thermally stable at the deposition temperature that you want to use. And because ALD is a self-limited process where you form essentially a monolayer of a species on the substrate, and then anything else doesn't stick very well. So you're limited by a monolayer, and if your precursor is decomposing when it hits the surface, you lose the layer by layer growth mode, and a lot of the attributes of ALD are gone. And so that's a second very important one. And then the final important component to an ALD precursor is high reactivity toward a second reagent to give the desired material. And so traditionally in oxide ALD, people would use water or oxygen or ozone, but increasingly now, all sorts of other materials are being, asked to be grown by ALD. For example, metals, which is one of the areas that I work in. Metals require typically reducing co-reactants.
Mm-hmm.
So there's a lot of chemical challenges in matching the, finding a co-reactant that is just right for the precursors that you've made. And going back to trimethyl aluminum, trimethyl aluminum is a beautiful, precursor because number one, it's highly reactive. Okay, so if you use water as the co-reactant, you're all set. Water and trimethyl aluminum are extremely reactive toward each other. Trimethyl aluminum has a reasonable thermal stability. I think it's thermally stable up to about 350 degrees C from what I can see from our experience. And it's a liquid. And one of the desirable attributes that we like in ALD precursors is to have it in the liquid state when it's being delivered in the gas phase, because the liquids have constant surface areas, and so you get a relatively constant gas phase concentration over the whole load of a bubbler. Whereas if you have a solid, you can get sintering and change in the surface area over a bubbler fill. And so I think it's around, I probably got the number wrong, but it's around 10 torr at room temperature, which mm-hmm. is, so it's just a perfect precursor.
So you mentioned these three requirements for having a good precursor: volatility, thermal stability, and then reactivity to a co-reagent. When you are thinking about a new precursor that you're trying to design for a particular process, all of these have to work together to make the precursor. But do you focus on something, the most difficult or the weakest link of these? So trying to find something that is thermally stable before you are looking at the other properties.
So the first thing is you want to eliminate all, low energy decomposition pathways whenever possible. So one of the simplest decomposition pathway is if you have a neutral ligand, a neutral donor ligand in a precursor, loss of that neutral ligand upon heating is often very facile. And one very common neutral ligand is a carbonyl ligand, CO ligand, in metal complexes. And many metal carbonyls have been, successfully used in ALD, but they tend to have some of them will decompose even on gentle heating. But the most robust ones are, begin to lose carbonyls at around 180 degrees C or in that temperature range. So, in our work, we've tried to avoid carbonyl ligands. We like nitrogen donor ligands, and there are certainly many oxygen donor ligands in use as ALD precursors. They tend to be less reactive. The pKa of an alkoxide is around 16 or 17. pKa of water is 13 or 14 or 15 maybe, something like that. So there's not a really strong reactivity there, whereas if you use an amide, the pKa's are above 30, so you get a very exothermic reaction with water. So the nitrogen-based ligands tend to make more reactive precursors.
Is there any type of modeling that you do at the beginning? Has the process from when you first began designing precursors evolved with new technologies, or is it still just chemistry works? This is organic, so we're going to use it.
So I think I have over the years I've developed a good predictive ability of what should be a good precursor and what might not be. My dream would be that someday you would be able to work with you would have a material that you want, that with a set of specifications like lowest possible carbon levels or resistivity level or something like that, and then in conjunction with a computational person, the experimental and computational people would be able to work back and forth and arrive at a very well-defined set of promising compounds, and then make those compounds and actually test them.
Yeah, that was something I actually been thinking about today as I was thinking about what we might talk about, and how often you are taking a material that you want to deposit and thinking about the material itself and the properties that you want way back at the beginning of designing the precursor, or if that is just it's just too difficult, too many steps removed, and you really need to just make something and test it out before you can get to that point.
So the way that I try to design projects is I would like a material that is where there's not a good current ALD process for it, and where there's a very clear end use, high value added use for the final material, and then I work backwards from that. So I like challenging materials, like molybdenum metal, for example, is a challenging material. Cobalt metal is challenging. Titanium metal.
Yeah, let's talk about some metals then. I know you have specialized in metal ALD and designing these precursors for metal ALD, and you're doing a lot of reduction chemistry. You're making other precursors that are reducing agents for these metals for multiple reasons. And I was hoping you could kind of walk through what these typical mechanisms are, because they're not exactly the same as the aluminum oxide ALD, where you're depositing one co-reactant, the next co-reactant, and making a binary material. These work a little bit differently.
Oh, I'll give you two examples, okay? And one of them is a little bit older from my group, which is cobalt metal ALD. And so about 12 years ago, we prepared a series of transition metal compounds, cobalt included, that contain diazodienyl ligands. Okay, they're cobalt-2 precursors, so they have two diazodienyl ligands. And it had been well established in the inorganic community that these diazodienyl ligands exist as radical anions. So that means that the ligand has a negative charge and it has an odd electron on it. And I looked at those complexes and I said, wow, I'll bet if you heat those, that odd electron on the ligand might get donated back to the metal at some temperature to give cobalt metal. Now that's a CVD process, but we made these compounds. We showed that they were volatile. we looked at their thermal decompositions, and indeed they give the metals. And so then I said, okay, wouldn't it be nice if we could figure out how to make these things decompose at lower temperatures? The original idea that we had was to find co-reactants that would cause the surface-bound diazodynyl precursors to decompose. And through just persistence and luck, we found that things like primary amines, like tert-butylamine, would cause the surface-bound DAD precursors to decompose to cobalt metal. And what we proposed was that you have the cobalt 2 is with the DAD ligand is tetrahedral, and that when our proposal was that the tert-butylamine will come into the surface-bound species and try to coordinate to the tetrahedral cobalt center, and when it does that, it causes a distortion in the geometry, which then changes the metal ligand bonding and leads to decomposition to give cobalt metal plus the diazodynyl ligand, which is evolved as a gas. The other aspect of that, which is that process is very selective for metal substrates over insulating substrates, which is quite a potentially useful feature of the chemistry. The second area is more recent for my group, which is the aluminum metal ALD.
Mm-hmm.
And so what we've done is look very carefully at aluminum ALD, and alane, ALH3, can be stabilized with an amine base like trimethylamine. So alane trimethylamine is a very well-known CVD precursor to aluminum metal. And what it did is what it does is it decomposes at around 60 or 70 degrees C to give aluminum metal and hydrogen and the amine. So what we said was that, well, if we had a more thermally stable aluminum hydride, then that aluminum hydride then could serve as a reducing agent for surface-bound metal halides.
Mm-hmm.
And so what we did then is we started doing synthetic work on aluminum hydrides and trying to find thermally stable ones. But the ones that we reported include a bidentate nitrogen, so an amido-amine ligand with two hydrides on the aluminum. And these compounds, we found one that appears to be a monomer. It's volatile. It's a very low melting point. I think it's got a melting point at around 32 degrees or something like that, and very easy to deliver. And if we use aluminum trichloride as the reactant, the ALD reactant with the hydride precursor as the co-reactant. Mm-hmm. What we think is happening is that we transfer hydride from the aluminum, the amido-amine aluminum hydride to the surface-bound, aluminum species, and then once you replace the chlorides by hydrides, you get instant decomposition to aluminum metal. So that was a chemical process then for depositing aluminum metal, and it worked beautifully.
And at what temperature does this aluminum hydride decompose? Is this a low temperature process?
So the precursors that we've reported decompose at around 180 degrees C. So we see ALD windows up to about 160 or 170 degrees C with those precursors. So we get an ALD window of 100 to 160 degrees for aluminum ALD. So, but the aluminum is beautiful, and that gave like almost bulk resistivity film. So,
and so when you're doing this process, it's aluminum trichloride that's bound to the surface. So you have metal halides on the surface. Then you have a ligand exchange, which ALD people should be pretty familiar to. Then when this aluminum hydride on the surface decomposes, does that have any effect on the quality of film? I'm thinking of, is it a complete decomposition of hydrides on the surface? Is there any left over for the next cycle that might cause diffusion in and out of the film?
unknown. All I can say is that we were able to characterize our films, and we observed low resistivities, which is a hallmark of high quality aluminum metal. You think about the trimethyl aluminum plus water ALD process that has been extensively studied mechanistically, and there's still probably a lot of ambiguities about growth. So something like the aluminum process, where you have a complicated co-reactant and surface-bound aluminum chlorides, that's a very complex system, and I think it would need a lot of work to understand it.
What other metals are you working on the horizon right now? Are there any very important industry relevant ones that people are desperate to have some processes for?
I'm interested in titanium metal. Titanium metal is very difficult because it's hard to reduce the titanium ion to titanium metal. It's about the same level of difficulties, the same electrochemical potential as aluminum metal. We're working on that, and our goal in that project is to make cobalt titanium alloy films, which are a very interesting material for barriers and for liners, ultra thin barriers and ultra thin liners. We're also interested in some other metals, zirconium and hafnium, and I think that those are interesting just because they're similar to titanium, and to my knowledge, they've never been deposited by ALD. And then a couple of metals we're interested in: rhenium. I've given talks on that. I'll publish papers soon. Rhenium is a very heavy, dense metal. It doesn't have a lot of surface mobility, so there's a lot of interesting properties that might come from that. We're interested in molybdenum and tungsten. Molybdenum is a very hot metal now. It's very difficult to deposit by ALD because it loves carbon and nitrogen. So any ligand that you make has carbon and nitrogen in it, and hydrogen. So these are things that we work on, and I like things that combine precursor development with ALD growth.
Is there a favorite precursor of yours that you've developed over the years that you just think the chemistry of designing it was elegant, it works well for ALD?
I chose the two, probably my two favorite examples: the cobalt metal from the diazodynyl precursors, and then the aluminum.
Your processes and your precursors you developed, have you went to producing any of these at scale? Are there any that have been a Strem knocking at your door to purchase some designs?
So I have about 30 issued patents, and that includes the foreign filings and all that. So each case has a series of foreign filings, and I think at current I have 4 licensed patents, and the diazodynyl precursors are currently available commercially from Strem Chemical Company, and then also from for microelectronics customers, they're available through EMD Performance Materials too. And EMD Performance Materials has several other of my precursors, and then BASF has has licensed the patent on aluminum ALD. So I do, if we've done something useful, I enjoy the patent protection process. It's fun for me. It's fun for the students, and it's exciting.
I commend the synthesis work because I come from an ALD lab where we have one hot plate in the lab. There is not a Schlenk line in sight. You know as good as I do where you might find a round bottom flask. I imagine, especially in your lab, there has to feel some immense control around your processes and the ability to tune them and impart new properties into films and compounds that you're setting up.
In our laboratory, I actually prefer to have precursors that were made in our laboratory, that were purified in our laboratory. The history of the precursors, because if you run into any problems, then you have to track back and find out where they came from. So and so I like having control over the precursor synthesis.
Yeah, that's great. And then, if you were never a scientist, you were never got into ALD, what do you think you would be doing these days? What would have been your plan B?
So I think I would have ended up being a patent lawyer, and I enjoy writing. I'm good at it, and I think it's an interesting field. So and part of that has been all the exposure that I've had with patent attorneys over the last 30 years working with, crafting patent cases. But I think it's very interesting. And I think I would have gone to law school and become a patent attorney.
The patent language, it's not too dry, too straightforward for you.
Well, when you look at the patent attorneys have they have a formula for writing these patents, and each section is important, and it's not fully clear to me what each one of those achieves, but they know what's going on. And then when you write claims, that it's an art to write claims, and so I think that's all very interesting.
Yeah, that's great. Well, Chuck, thank you so much for joining me today on the ALD Stories podcast. Do you have any place or website, social media that you'd like to shout out? We can put it in the description on the video below, and any place we can find you, your students, and the work.
The only thing I have is I'm not a social media person, so the only thing I have is my lab website, which is we're in the process of updating now, but people can check on that on a regular basis. So.
Perfect. We will put the link in the video below, in the description below. However YouTube works. Okay. But thank you again for joining me today. Thank you everybody who has tuned in to listen to another episode of ALD Stories, and we will see you next time.
Thank you very much, Tyler.
Cool. Chuck,
all right.
That was great.
You're listening to ALD Stories with Benek, the home of ALD. To stay tuned for new episodes, make sure to follow us on Spotify, Google Podcasts, or Apple Podcasts. We hope you enjoyed today's show. Talk to you in the next one.